So far, we've done translations, reflections, and rotations all individually. Today, we're just going to combine them. So instead of having our original coordinates and then our new coordinates, we're going to have a first set of new coordinates, which is going to be our first transformation, and then we're going to have our second set of new coordinates, which is going to be our second transformation. So an example of this is if we were first given a reflection and blue is our original pentagon. Well, then we would reflect it across this line. This would be shape 2. So shape 1, then shape 2, and then this would be shape 3 because it's then translated across. Or if blue is still our first pentagon and then we translate first, we get here, and then reflecting gets us here. Sometimes when you're doing transformations, the order doesn't matter and you end up getting to the same spot. Like here, we did a reflection first and then a translation. However, if we do the translation first and then the reflection, we end up getting to the same spot. That's not always the case. So looking at this first problem, we're given triangle ABC with points A, points B, and point C. So let's go ahead and fill those in for the coordinates. So the original coordinates are 3, 2, 6, 3, and 7, 1. Now we're given that first we're going to translate. So that's going to be our first thing. Or actually, I'm going to go ahead and I'm going to do it in a different color. So our first transformation is a translation. And that's going to subtract 3 from all the x's, but it's going to keep the y's the same. So here, 3 minus 3 is 0, and we keep the y's the same. 6 minus 3 is 3, and we keep the y's the same. 7 minus 3 is 4, and then we keep the y's the same. Now here, for our second transformation, we have a reflection in the x-axis. Now if you don't remember the coordinate rules for reflections, here they are, and just paste it in. So if we look, whenever we have a reflection in the x-axis, whatever the x and y coordinates are, we keep them in the same position, and we just negate the y. So here, we're going to keep everything in the same position, so 0, and then instead of 2, we're going to put a negative 2. And then we're going to keep 3 in the same position, but instead of the next 3, we're going to put a negative 3. And then keep 4, but instead of 1, we're going to put a negative 1. Up to this point, we should be able to do original coordinates to some kind of first set of new coordinates, whether it's translation, reflection, or rotation. That's what we've been doing the past few days. The step that we do next is kind of the exact same thing. We're treating these like our original points and doing some kind of new transformation to them. So now that we have all 3 sets of our points, we just need to graph them. So A is at 3, 2 here. B is at 6, 3 here. And C is at 7, 1 here. Then A prime is at 0, 2. B prime is at 3, 3. And C prime is at 4, 1. It makes sense that from the blue shape to the purple shape, it didn't rotate or it didn't reflect because the only thing that we did was a translation. All we did was move it left 3, which is exactly what it looks like. And now for our next shape, we have 0, negative 2 as the first coordinate. So that's going to be A double prime. And this is some notation I don't think we've got into yet. But just like we put 1 prime symbol to show that we went from A to some kind of transformation from A, whenever we go from A prime to a new transformation, we're just going to put 1 more prime symbol. And then if we were to go more beyond this, we would just keep adding primes. Our next point is then 3, negative 3. And that's B double prime. And then our last point is 4, negative 1, which is C double prime. And then this looks exactly like we just reflected this across the x-axis, which is what it should look like. Moving on to the next point here, we're going to graph a line. So only 2 points. It's a little bit easier this time. we're given that the first point is at 1, -3, and the second point is at 2, -6. So the original is at 1, -3, and then the second point is at 2, -6. We're given that our first transformation is a reflection. It's a reflection in the y-axis. So if we go back and look at our little chart, a reflection in the y-axis means that if we have x, y to begin with, we're going to keep them in the same position, but just negate the x. So instead of x, y, this becomes -x, y. Applying this to these coordinates, instead of 1, -3, this becomes -1, -3. And instead of 2, -6, this becomes -2, -6. Our next transformation is a rotation of 90 degrees about the origin. Now, about the origin doesn't say clockwise or counterclockwise. So just like we covered yesterday, if it just says 90 degrees, we're going to assume that's counterclockwise. That means we can use our chart for degree of rotation and see that if it's 90 degrees, that means we're going to flip the x and the y, and then we're going to negate the y. So x, y becomes -y, x. All right, well, first let's look at the -1 because that's the x. That's going to go here. And the -2 for s prime is going to go here. Now we have to negate the -3. That means we're going to make it 3. We have to negate the -6, which means it's just going to become 6. Well, now we have all of our points, so we just have to plot them. These are our x coordinates on the left, and then our y, our x and our y, and then our x and our y. Just as a quick reminder, x is how far left or right you move, and then y is how far up or down you move. Left for x is going to be your negative, and then right for x is going to be a positive. Up for y is a positive, and down for y is a negative. So here for this first point R, it's at 1, -3. So that means we're going to move 1 in the right direction, because this is the x coordinate and it's positive, and then 3 in the downward direction for y because it's a negative. So 1 to the right and 3 down from the origin. You always start from the origin when you're plotting points. So actually plotting these, we have 1, -3. This is point R. And then 2, -6. This is point S. So this is line RS. And then plotting our new points, or our first set of new coordinates, we have -1, -3. This is R prime. And then -2 and -6, which is S prime. And it looks kind of like we reflected across this y-axis, which is exactly what we did. So we're good to go. Now our last points are 3, -1, and then 6, -2. This is going to be R double prime, and then S double prime. Now, remember, 90 degrees goes counterclockwise, so that means we had to go counterclockwise here by 90 degrees to get from this R prime, S prime to this R double prime, S double prime. By the looks of it, that's exactly what we did, so we're good to go. So these are the 3 things that you need to have plotted, is RS, R prime, S prime, and R double prime, S double prime. Something else that we have not talked about is called a congruence transformation, or a rigid motion. This is when you have a translation, reflection, or rotation, or combination of them, where the actual size and shape of the image does not change. So for example, if I have a box here, and I just move it to the right, and let's just say this box is the exact same. Again, I'm not an artist, but let's just pretend those are the same box. The box didn't change in shape or size, so that would be considered a rigid motion. So we would say this is a rigid motion. However, if I have a little bitty triangle here, and that becomes a big triangle, well, that's a dilation. And a dilation does change the shape. So because they are no longer the same size, they are no longer a rigid motion. So it is not a rigid motion. So I'm going to put rigid motion and then a little X. If we have any combination of translation, reflection, or rotation, and only those, then we have a rigid motion. Because let's think about it for a second. I'm going to do some examples. First, we've already done a translation. That's here, this little box here. This is translation. We know that if we move a shape using a translation, it's not going to change the shape or the size. It's just going to change the position. How about a reflection? So let's do another triangle. Let's say we have this triangle here, and we're going to reflect it across this line. Well, reflecting it across gives us this triangle. We're going to pretend those are the same triangle because, again, I'm not an artist. But they are the same shape. One's just flipped over, but I mean, it's still a triangle. And they are still the same size. So because it's the same shape, and because it's the same size, a reflection is a rigid motion. Similarly, think about a rotation. Let's say we have this triangle right here. And this triangle, we're going to rotate it to where it's laying down flat. Well, even though it's laying down flat, it's still the exact same triangle. We kind of just move the position of it, but it's still the same shape. And it's still the same size. So because of that, a rotation is a rigid motion. So here we're given a whole bunch of different shapes. We're given squares and we're given triangles of different sizes. And it's asking us identify the congruent figures. Well, congruent, that just means equal or the same. And then it says explain why they are congruent using transformations. Now we know there's a thing called a congruence transformation or a rigid motion. Now, a rigid motion is if you can get from one place to the other only using translations, reflections, or rotations. So, the trick is, can we get from the first shape that it gives us to the second shape that it gives us using only translations, reflections, or rotations? If we have to use a dilation to get from one shape to the other, it is not a rigid motion, and therefore the shapes are not congruent. So first it says triangle JIH and triangle UTS. So triangle JIH is this one right here. It's the one that starts at J and then goes to I and then goes to H. And then it says triangle UTS. So this one right here that starts at U, then goes to T, and then goes to S. Well, first, do we know if those two are the same size? Well, this is a side length of 2. This is a side length of 2. And then triangle JIH has a side length of 2, and also another side length of 2. We're going to get into special right triangles later, but because this is a right angle here, and these two sides are the same, these hypotenuses here are going to be the exact same. So we know they're the exact same size, and they're both clearly triangles, so they're the same shape as well. What we're going to do is we're going to look at rotations. Now remember, a rotation has some specific rules to it, and here they are. This point J is at negative 1, 2, 3, 4, 5, and then 1, 2, 3. So J is at negative 5, 3. And let's look at point U. This is at 1, 2, 3, 4, 5 here. And then negative 1, 2, 3. So this is at 5, negative 3. And if we rotate one point in the shape, we're going to rotate all of the points. So we're going to see if just this one point on each of the shapes can match. Well, the X and the Y look like they stayed in the same position, and then it went from a negative 5 to a 5. So the X changed, the X was negated, and it went from a 3 to a negative 3. So the Y was also negated. So we need to look at a rotation that keeps the X and the Y in the same position, but it negates both. So if we go up here to our chart, no, 90 changes them. 180 seems to match it perfectly. The X and the Y stay in the same position, and you negate both. Let's check 270. Nope, those flip, so 270 is out. 180, however, perfectly matches it. And we can check. To go from this quadrant to this quadrant, that's a 9-degree rotation. But that would leave us here. We don't want that quadrant. We want the next one. So we have to do 90 more degrees, which would give us the right quadrant, and we already know the coordinates match. And so it seems like all we need to get from triangle JIH to triangle UTS is a 90-degree rotation about the origin. This next one's going to be a little bit easier because you can see it kind of better. We're going to have triangle GEF and triangle MKL. So let's look at triangle GEF here. GEF. And then triangle MKL. Well, just looking at that, they kind of look like the same triangle. But let's just check. So here, this is 3. Here, and this is 3 as well. They're both 3 boxes long. This one is 2 boxes high. This was also 2 boxes high. Hey, so far they kind of match. They're the same shape, they're both a triangle, and they're the same size. Now, is there one or more rigid motions that we can use to get from one triangle to the other? Well, if you look, point G is 1 box away from the x-axis, and then 1 box away from the x-axis in the other direction is box M. Well, look at E. E is also 1 box away from the x-axis, and if you go 1 box in the opposite direction, you get to point K. So it looks like we're just reflecting across the x-axis. Let's look at point F. If we do 1, 2, 3 boxes to the x-axis, and then 1, 2, 3 boxes in the opposite direction, we'll get to point L. So yeah, everything checks out. This is just a reflection. So to get from triangle GEF to triangle MKL, we're going to use a reflection, and then we reflect it across the x-axis, because that is the horizontal axis here. Now our last shapes are square ABCD and square NPQR. That is these 2 squares right here. Now we can look, both these squares are a 2 by 2, so that means they're going to be the exact same size, and I mean they're both squares, so they're both the same shape. Let's look what the question asks us. It says we can map square ABCD onto square NPQR using a something along the vector something. This goes back to day 1, and we only ever used the word vector with translations. So here, we know this has to be translation. Now the trick was, do you remember what we put here? This is a different kind of notation. In this first spot, where normally you would put an x value, this is your change in x. Now if this is your change in x, well then this would be your change in your y. So we see, did we go left or right on the x, and how far left and how far right? And then for the y, did we go up or down, and then how far up or how far down? And because it's a translation, That means every single point is going to move the exact same amount. So we really only have to just find how far one singular point moves. So because there's a whole bunch of writing here and here, I'm going to use point P. Point P seems like it would match up with what's the top right point. So it's going to match up with point B here at the top right point. So all right, B goes down to here. So let's see how far we have to move P to the right. We have to move P to the right 2 boxes. So that means it's going to move positive 2 in the x direction because it moved 2 to the right. And then how far up did we have to go? Well, 1, 2, 3, 4, 5, 6. So up 6. Up 6 means that we put 6 here in the box for y. Our next thing that we're going to get into is similarity transformation. And a similarity transformation is kind of like the definition of a congruence transformation, where it defines a combination of transformations that we do. But congruence is specifically only translation, reflection, or rotations. It is everything except dilation. And then similarity transformation has to include a dilation. And when it says it preserves angle measure, but not side length, that sounds kind of weird. And it gives you a picture, but the picture also kind of looks weird. So what I'm going to do is I'm going to kind of scroll. We're going to ignore some of this wording. And we're going to go down and we're going to draw our own picture. The easiest thing that I found to represent this is triangles. So let's say we've got a triangle like this. And then I'm going to say that this degree measure is, let's say, 30 degrees. If our transformation is a dilation, that would make this triangle bigger. So what if the triangle instead was this shape? That's clearly a bigger triangle if it was the purple one. However, this angle would still be 30 degrees. You can see it just goes off of the exact same angle. So that's what it means when it says it preserves the angle measure but not the side length, because clearly this purple side is a lot bigger than this red side. And once we have this purple triangle defined, we could then move it. So if we were to do a rotation, let's say, and then we rotate this triangle, this would be what, 270 degrees? Nope, I lied. That's going to be 180 degrees. Sorry if you're writing in pen, my bad. But even though we used a rigid motion of a rotation of 180 degrees, because we combined it with a dilation, it's no longer entirely a congruence transformation. It is now a similarity transformation. I know it's a bunch of words, but the pictures make it a lot easier. At least, hopefully they do. Our last thing that we're going to do is we're going to graph a similarity transformation. So we can see that our similarity transformation is made up of two things. So first, it is a translation, and then second, it's a dilation. And because we have a dilation included, that's what makes it a similarity transformation, not the fact that we have a translation already in there. Let's go ahead and write our original points. We have triangle ABC, so 3 points, A, -4, 1, B, -2, 2, and C, -2, 1. So A is -4, 1, B is -2, 2, and C is -2, 1. Then we have a translation where we're going to take our x and take our y, and we're going to add 5 to all the x's, and we're going to add 1 to all the y's. Super easy. It's just a translation rule. So -4 plus 5 becomes 1. That's an ugly 1. There we go. 1 plus 1 is 2. -2 plus 5 is 3. Because all the x's are adding 5 to, and all the y's are adding 1 to. And then 2 plus 1 is 3. -2 plus 5 is 3. And then 1 plus 1 is 2. So this is our first set of new coordinates. Our second set of new coordinates is a dilation. And I know we only covered dilations yesterday, so this still might be fresh in your mind. But whenever we have a 2x here and a 2y here, this just means times 2 for whatever coordinate you have. So we're going to multiply all the x's by 2 and all the y's by 2. Simple enough. And it's kind of easy because we have small numbers. So for a prime, 1 times 2 is 2. And then 2 times 2 is 4. For b prime, 3 times 2 is 6. And 3 times 2 is still 6. For c prime, 3 times 2 is still 6. And then 2 times 2 is always 4. This gives us our 3 sets of coordinates to draw our 3 triangles. So first, I'm going to draw the original triangle at coordinates -4, 1, right here. This is point A, and then -2, 2. This is point B, and then -2, 1. This is point C. We have a nice little bitty triangle right there. And then we do our first new triangle, our translation. That's going to be at points 1, 2, and this is A prime, and then 3, 3. This is B prime, and then 3, 2. This is C prime. And we have another nice little bitty triangle. And then our final triangle is going to be A double prime, B double prime, and C double prime. I'm also going to draw it in red. So 2, 4. And then that's A double prime. B double prime is at 6, 6, right here. B double prime. And our last coordinate is 6, 4, right here. That is C double prime. And if we connect these, but we don't cut through B prime, then we get a big old fat triangle. Again, just to recap, this is considered a similarity transformation because it had a dilation in it. And you can see, even though the angle is the same here, the side length changed. Similarity transformations have to include a dilation, and they have to preserve the angle measure. So think about the small red triangle going to a big purple one. It's still the same angle measure, but it's a different side length because the purple side is bigger than the red side. We also checked about checking whether a transformation is a rigid transformation by seeing, can we get from one place to the other by a rotation, a reflection, or a translation? And we also graphed composites of transformations. We talked about congruence transformations, and that for something to be a congruence transformation, it has to keep the same shape and size. So any combination of translations, reflections, and rotations will be a congruence transformation, or you can call it a rigid motion. But don't you dare put a dilation in these. And then we also started off the lesson by graphing composition of transformations. Let me know if you have any issues with this. My emails are open. You can contact me on Student Square, and I will be happy to answer any questions you have.